Okay, we're now recording. Let me try to explain Napat's question. Okay, let's say your question is, how do we know if it's going to be positive or negative, right? So let me give you some examples. This is fun because it's about understanding the structure. Let's say like this. I'm going to erase this. Okay. Let's say if I have something like this and I push this with a load here, a load. What's going to be our deformed shape or deflected shape? Your structure should, your structure is going to come down like this, right? And perhaps does this. Now it's kind of easy to see. So you should be able to say, okay, for sure, this one is going to be clockwise. This one is going to be counterclockwise, right? And say, if I do this, same beam, but this time I push it here with the equal load. Now, this one has to come down, right? Because of the load. This one too. And because the load, the two loads are equal, so they should come out the same. And does that. So now you can say, yeah, I know this one is going to be counterclockwise. This one should be clockwise. But let's say if the situation gets more complicated. Let's say something like this or this, and you don't really know for sure how much, maybe the load is pretty much the same and so and so. So now you don't know what's going to happen. You can only guess. If you want to try to predict the result ahead of time, it may occur like the first one. If the it may occur like this. If the point loads are way heavier than the uniform load in the middle. Because it's, think about it as something natural. Your huge friend standing here, and then your small lady friend, you know, lying down there. If that would be the second case, right? So it could happen like the second one. But let's say if the uniform load is very, very, very heavy, and these 2 points are alike, so the first one is going to occur. So it depends on the relative load as well. And sometimes if I do something more dramatic like this, and then my internal span is like very, very tiny together, like this, and say put the equal load on them. Now chances are, you know, because this is so short, and when you consider the stiffness, it means that this one is pretty stiff. The chances are it's going to go down like this, and then, you know, too stiff to have the double curvature. So it's just going to be like that. If you can see this before your calculation, great. But if not, the results will tell you whether or not your rotation is clockwise or counterclockwise. You can see from the numbers by yourself. But in this example, it just so happens that everything is similar. The span length, the load. So the only way, because the load are equal, the only way for you to have symmetry is that the rotation must be 0. Okay, so if we can take advantage of the symmetry from the beginning, you see that here you can take advantage of this, and now you should know that MBC is going to be exactly the same and opposite to MCB as well. So if you are going to take advantage of symmetry, you can your work will stop here. Because you only have one unknown now. If you take advantage of symmetry, correct? That is zeta B. And you know that zeta C is equal to minus zeta B if you take advantage of symmetry. So you only need one equation, sigma MB equal to 0. So now you can solve zeta B. But you have to see the picture. You have to understand the nature of symmetry. Because some would want to take advantage of symmetry, but they say zeta B equal to zeta C. It just, say carelessness. Because zeta B equal to zeta C mean they rotate in the same direction. So it's going to be exactly like what Napat just drew. If zeta B equal to zeta C, that means this is the line, right? They must either be clockwise or counterclockwise. And this is not symmetry. This is anti-symmetry. So good engineers have to be lazy, so they say. And in order to be lazy, you must know how to take advantage when it presents itself to you like this. It's symmetry. So I'm too lazy to do it. I'm just going to write one equation because I know zeta C is equal to minus zeta B. So my work ends here. One equation, one unknown. Like I say, in less than 5 minutes, you can actually solve this B. Okay? So now you have solved the unknowns. It's time to go back to calculate end moments. So because now we know that the zeta B and zeta C are 0, it might as well say that, moment is equal to fixed moment. Correct? Because you can see that when it's 0, this term is 0. So MAB is exactly minus 3600. MBC is 3600. And MCB becomes, BC becomes minus 3600. Remember, whatever you do, when you check back, your equilibrium equations will always be satisfied. So we can now say MAB equal to MBC equal to MCD equal to minus 3600 kilogram meter, and then MBA equal to MCB equal to MDC equal to 3600 kilogram meter. Okay, and what you should be able to do next is, of course, the reactions. Now from this, remember I used the clockwise positive sign convention. So I can draw the free body diagram of member AB now. I have MAB is minus, so it's counterclockwise. That's my moment. And MBA is positive, so it's clockwise. And I also have my uniform load, 1200 kilogram per meter. So you see the moment will cancel each other out. So basically your reaction becomes WL over 2, right? Because the moment, they are equal and opposite. So right here you have 6 meters. So basically this is 3600 and then 3600. See how easy that is? So it's going to be the same for member AB, BC, and CD. Okay, they are the same. So that means you can easily draw your shear force diagram because they are all the same. 3600 here, Going down the same, going up the same, going down the same, going up the same, going down the same. Special case. Right? And now your bending moment diagram. Remember, you have your end moments already, and that here is counterclockwise. So this is the sign convention of the negative moment when you draw the bending moment diagram. Remember, this is based on clockwise positive, you know, clockwise positive. So when you draw the bending moment diagram, you must use the sign convention for bending moment diagram, right? And when you have this, it's frowning beam. So that is negative moment. Minus 3600, minus 3600. And the same here. Shear force diagram, that's bending moment diagram. The end of the problem. Very easy, right? Compared to the good old force method. Even, and if you can take advantage of symmetries, see how quickly this problem will end. Any question? You are quite surprised how easy it is, right? Any question? If not, let's move on to the next example then. See, the next one would be more like typical problem because it's not symmetric. So that means it's a full-blown problem that you have to do everything. Okay, so you ready for that? This is the old examples that I've been using for quite some time as well. So now step number 0, if we are going to begin. Unknowns. Sorry, degree of freedom. Let's give them a conventional name, A, B, and C. How many degree of freedom, folks? Can anybody tell me?
2.
Okay, they are?
2.
Yeah, I know. They are. Can you say that what they are? Those two?
Okay. Zeta B and Zeta C.
Okay, good. So Zeta B, oops. Zeta B and Zeta C, they are your two unknowns. Very good. So now we have established that. We know we have to construct two equilibrium equations, right? So we go to step number 1. We try to figure out relative stiffness. You don't have to do it. You can just use I over L. That's fine as well for those who cannot really manage the least common number. Okay? So now KAB is I over 3. KBC becomes 2.5 I over 5 or I over 2. Oh, now we don't have things that are equal anymore. So I'm trying to find the least common number. So I can multiply this by 6, right? So I can say if K equal to I over 6, I'll multiply everything by 6. So this becomes 2K, and this becomes 3K, relative stiffness, okay? Because this is I over 2, this is I over 3, so BC is slightly stronger than AB, right? Judging from the I over L ratio. So for those who mess this up, it's really sad because you can't tell which member is stiffer than which. It's a comparison of I over L. This is I over 3. This is I over 2. Which one is greater? Which one is stiffer? It's I over 2, right? So I just multiply everything by 6. So I got 3K and I got 2K. So that's my relative stiffness. So for those of you who are really confused by this, you can just stick to I over 3 and I over 2. That's fine because it's relative. So I over T and I over 3 and I over 2, they are relative as well without having to do this. But I prefer to do it. Gives me a better picture. Next, fixed end moment. Now we have quite a lot. F, E, M, A, B. You see that it's not in the middle. So the formula here, let me try to write it down here. Let's call this A and B, and the length is L and the load is P. This one is minus P A B square over L square. This one is P A square B over L square. And someone still get it wrong. Believe that. So FEMAB now it is minus P is 9 tons. A is 2. L is 1. B is 1. B square over 3 square. So this is minus 2 ton meter. FEMBA now. It is PA square B. P is 9. A is 2 square. B is 1. And L is 3 square. So we have 4 ton meter. Next is fixed end moment of BC, and again it's uniform load. So this guy is minus W is 2.4, L is 5 square over 12. This is minus 5 ton meter. FEM CB now, it is positive 1 because it's clockwise, so it becomes 2.45 square over 12. So this is 5 ton per meter. Okay. So now we move on to the next step, that is slope deflection equation. We should start from AB, right? Yeah. M A B, it should be 2 EK. And now I use my relative stiffness, it becomes 2K. 2 zeta A plus zeta B minus 3 psi A B. And I can just write my fixed moment right away, right? Or I can wait. FEM AB. So this is 0. We don't have any joint displacement, 0, and this one is minus 2. So the equation becomes 4 EK zeta B minus 2. Okay, pretty simple, right? Oh, I should write the name here, SD equations. Now let's move on quickly to MBA. Again, it's the same member ABBA, so the K is 2K. This time 2 theta B plus theta A minus 3 sine AB plus F E M B A. So now we know theta A is 0, psi is 0, and this guy is 4. So this one comes out 2 and 2 and 2. So we have 8 EK theta B plus 4. Okay. Let's move on. Am I going too quickly, guys? Hope not. Okay.
No.
Okay, thank you. Thank you. MBC now. So now we move on to the next member is member BC. So the stiffness is going to be different. So it is 3K now, right? 2 theta B plus theta C minus 3 psi BC plus F E M B C. Nothing is 0 except the psi. As usual, I'm beginning to be lazy to write psi now, you know. And this one is minus 5. Okay. So, all right. 6 and 2, so that's 12 EK theta B plus 6 EK theta C minus 5. And MCB 2 E3K 2 theta C plus theta B minus 3 psi AB, okay, plus FEMCB. Again, this guy is 0 and this guy is 5. So now, okay, in order to keep things nice and tidy, I'm going to write B first. So that becomes 6 EK theta B plus 12 EK theta C plus 5. So now we are done with slope deflection equation, but there is another small matter which you have not mentioned. You probably know, and you don't know how to handle it. That guy. That is a free end. Okay. So you should notice that I do not count the degree of freedom here, because that is not a joint. That is a free end. Some students do count theta D, whatever. We don't need that. Okay, it's not a joint. It's a free end. And when you take a look at the free body diagram of the free end, actually, this, when I write something like this, this is my free body diagram, 2 tons, which means that I need to have this moment, right? And that moment arm is 1.5, the load is 2, so this moment has to be 3 ton-meter, correct? That is already a resisting moment, because this guy you can also replace with the moment. Correct? This load and this moment arm itself, in fact, they, oops, sorry. Thought I changed the color already. This is equal to 3 clockwise, right? So your internal moment to create the balance for this piece is -3. So that's exactly what MCD is. That's your MCD, right? -3. I can easily say MCD is minus 3 ton meter. Are you confused? Hope not. Okay. So is there any question? I'm going to rumble on now.
MCB for sine should be BC, right? You write AB.
Where?
Sine.
Sine?
Yeah.
Which one?
It should be sine
Oh, you're right, you're right. You mean here? That one?
Yes.
Right.
Yes.
Thank you. So it's BC, yes. See, that's the reason why I don't make my video public. It's natural to have errors like this. Okay. No more question, right? So it's high time we finish our equilibrium equations. So this is not the first time. So let me, you know, right in the short form. But now we have sigma MB, which is equal to MBA plus MBC equal to 0. So that gives you what? BA and BC, they are this couple, right? So when you write things in order, it's pretty easy to do the work because now B, they are together. So now 8 and 12. So I have 20 EK theta B plus 6 EK theta C, and then minus 1, right? $20 EK theta B, the 20, yeah, plus 6 EK theta C. My E is pretty bad, and my apologies. So if you can't read my handwriting, you have to let me know right away, you know. Minus 1 equal to 0. And then we have sigma MC equal to 0. And that is CB plus MCD equal to 0. So now we have 6 EK theta B plus 12 EK theta C. We have plus 5, we have minus 3, so it becomes plus 2 equal to 0. Again, my E looks pretty bad. The way I move my hand. Okay, so that becomes equation number 1, and that's number 2. Hang on for a moment, I need to go check something. I'm back already, so. Oh, I didn't pause the record. So it is recorded? Actually, yes, okay. Thought I hit the pause. Anyway, now it's just a matter of solving this equation. You can use your calculator, and your calculator should be able to handle 3 simultaneous equations, right? This is what they are called, simultaneous equations. And one thing that you should notice is, you see how things will always be similar. Because when you put this in the matrix form, you will now have something like this. 26, 6, 12. And then this is E, K, theta B, E, K, theta C. I can move this 2 to the opposite side. It's going to be equal to 1 and minus 2. These coefficients of your equations will form the stiffness matrix. Okay, and in order to solve this without any modification, let's say if we carry on things like this, you will always have the matrix that is, how do you call it in English? Symmetric in this axis, always. So after you've done your work on equilibrium equations, you can always check the coefficients, whether or not you have the symmetry like this. Okay, so now after we solve this by playing some calculation music, you will have EK theta B equal to 2/17, and EK theta C, it is now minus 23/102. So now you see from this that EK theta B is clockwise, EK theta C is in fact counterclockwise. You can check this to see if it makes sense. Theta B clockwise, is that possible? And C is counterclockwise. So that means this guy is pretty heavy, right? 2.4 tons per meter. You multiply that by 5, the total load is 12, right there in the middle. So it is possible that you're going to have something like this. Okay, so we got the answers. We plug them back in our slope deflection equation here. So you're going to get everything. So number 5 now. In moments. MAB. One more thing. If you don't use relative stiffness, just like I do, or you use different relative stiffness, these answers will come out differently, but relatively, you know, they are the same. When you say compare the two of them, and in the end, no matter what you use as relative stiffness, the end moments will come out to be the same. So for MAB, it's 4, right? 4 EK theta B minus 2. So 4 multiplied by 2/17 minus 2. So that is minus 1/53 ton meter. MBA is now 8. Right, is it? 8 EK theta B plus 4. So that's theta B plus 4. That is 4.94 ton meter. MBC is how much? There, 12 EK theta B plus 6 EK theta C minus 5. 12 EK theta B plus 6 EK theta C, which is actually negative, minus 5. What do you expect here? Of course, it has to turn out exactly the same and opposite MBA, right? Why? Because this is what you use to solve your unknown, right? You say sigma MB equal to 0 here. So you better have sigma MB equal to 0 in the end. right? And now you know that your MCD here is -3. So MCB from this equation better be equal to 3, right? MCB is now 12 EK zeta C plus 6 EK zeta B plus 3. And ta-da, of course, it is 3. So your end moments are all correct because they all satisfy your equilibrium equations. And now you can proceed to calculate your reactions and so and so. Now we just have to have this. Now be careful, the sign convention, -153, so that's counterclockwise. 494 positive, so it's clockwise. And you also have the load, 9 tons. That's your free body diagram, right? Next one. Minus, so it's counterclockwise, 494. See how they all come in nicely. This is plus, so it's clockwise 3. And you have here uniform load, and then another one. That's a cantilever, right? 2, right? Yeah, 2, and that moment is 3. Okay. So now, just to drive you guys a little bit crazy, I can solve for reactions based on the load and then based on the moment. I can do them separately and I can add them up in the end. Can I do that? Can I do that? Nobody asked an answer. Huh? See, for example, let's take the one in the middle. Okay. If I look at the uniform load alone, this is 5 meters, right? Yeah, okay, 5 meters. So I know that my reaction to the load, that's basically WL over 2, right? So it's 6. 2.4 multiplied by 2.5, that's 6. This is the reaction due to the load alone, right? So now we consider the reaction due to the moment. See, they counter each other. So the reaction due to this moment, one has to go up, one has to come down to maintain equilibrium. When you look at this alone, right? You have 4.94, you have 3. So basically 4.94 is greater than 3. So that means this beam will come down. This beam will rotate counterclockwise. So I need clockwise reaction for that, right? And so maybe I should change the color. There, better. That is reaction due to the moment. So that means the reaction due to the moment here, because 4.94 is greater than 3, so you need a couple like this to help balance the moment. And therefore, this is going to be equal to 4.94 minus 3. That's the moment. To make it a reaction, you have to divide by the length of the member. Right? Can I do that? Don't have to take moment anymore, right? And then this will be exactly the same number, but in the opposite direction. And if you don't believe me, you can perform your calculation. And in the end, you're going to get the number that this is equal, because these two go in the same direction. So it's larger, 6.39. This one is 5.61. See, I just calculated the reaction. This is due to the load. And that is due to the moment. Can I do that? Do you believe in equilibrium? Do you believe in superposition? Nobody is talking at all. What is going on here? So the green one, this is 9 and the ratio is 2 to 1, right? This is 2, this is 1. So you should know that the reaction due to the moment, this is going to be 6. Oops, I thought I changed the color. Oh, yeah, actually, that's correct. So the reaction due to the load, this one is 6, this one is 3, right? No calculation required. And then reaction due to moment, because 4.94 is greater than this, so you need a couple that goes up in this direction and then down in that direction. And the magnitude is, of course, 4.94 minus 1.53 divided by the length, which is 3. Simple as that, right? And this guy, because the two components go in opposite directions, so you would expect the force to come out smaller, 1.86 up. And then here is 7.14. See, feel the structure, man. Okay, that's the end of it. I hope you can draw the shear force diagram and bending moment diagram by yourself. We have some space, yeah. So coming from this, I can in fact complete the shear force diagram. First member, it's going up 1.86, coming down 9 to meet 7.14, right? The second one going up 6.39, coming down 5.61, like that maybe. And this guy, nobody cares to complete this. Of course, the reaction here is 2, right? So it's 2 up and 2 down. Okay. The 0 lines here. Okay. And the bending moment diagram. You don't begin from 0, right? Because you have fixed end moment, so you have minus 1.53 here, and then you have another negative 4.94. And this, whether or not this is negative or positive, you need to check this area, right? This area will give you the moment, and in fact it is positive, comes out to be 2.19. And then you move, that's a point load. So the bending moment diagram is like that. This is the same, minus 4.94. This is the negative moment equal to minus 3. And then you're going to have bending moment diagram like that. This value again comes from this area. Okay, and value is 3 point, I can't read it. 57, I suppose. Okay. And then the last portion, of course, this one is simple. On a strip. Just like that. So that's it. Everything complete in time. This example is now complete. When you draw bending moment diagram, what you can actually do is, you don't have to draw them separately. It's a beam. You can move them like that, that your bending moment diagram, and your shear force diagram. Oh, missed it a little bit, Why is it really beautiful? Like that. Okay, it should be here. Fix it a little bit. Okay. And 5.61. That's that thing. Okay. And then that's 3. 2, sorry. Okay, that's it. Any question? Any question? Notice one more thing, ladies and gentlemen. We are now dealing with what we call a continuous beam. And please notice that you always have moment at the support. This is not the world of simple beams anymore. And notice that whenever you have a continuous beam, chances are when you draw the deflected shape like this here, chances are you are going to have negative curvature here. It's only natural, right? You cannot have a positive curvature because of the support. So your structure tends to bend down in a frowning way. So most of the time, wherever there is a support, the moment at the support is generally negative moment. Right? Because your positive moment is this curve. It can only occur at the, somewhere close to mid-span. And the negative moment, wherever you have the support, because your beam can only bend like that. So that is a negative curvature. So please keep in mind that if the loading condition is not, say, peculiar or, weird or whatever, this is exactly what you should always have, unless, of course, there's a strange case like this one that I drew, momentarily, like this. See that this one is okay. You can have a positive moment because you have the load in the middle, so your beam comes down with a positive curvature, the smiling face. But because the span on the external spans, these two, they don't have any load, so it goes up with a negative curvature. So you probably have the negative bending moment throughout this. See, it depends on how your beam is deformed. And like this, now you push the beam on the two external spans. So in the middle, it goes up. So you could probably have the negative moment throughout this member as well. And especially like this, when you have a short span, it won't come down, it goes up like that. So you will end up having a negative moment throughout this. So if you can somehow predict the deflected shape, it will help you see what kind of bending moment you are going to have on your structure as well. Okay, question? Hello? Folks?
Still here,ครับ.
Yeah, still here, but still here and crystal clear. Can we say that? I'm still here, but I'm crystal clear, so I don't have questions, right? except can we have a break?
As clear as crystal ครับ
Okay then. So let me stop the record.